started. Excellent. Okay, good. So today is November 17th. So we will continue to talk about the exciting optics and images there. Okay, and then in terms of the logistics, they remain the same as last time. And I hope that some groups, if you have not sent me the proposal for the midterm exam number 2, please quickly send that to me so that I can comment and improve your project for you. Okay. For the one, I already sent the comments that those projects, if you have further questions, you can talk to me further. I'm happy to revise it further for you. Okay. The proposal so far I received write very well. So and I see the improvement and the very nice descriptions from some groups. That's very nice. And also I look at your improved PPT slides. That looks very beautiful. Yeah, good projects. Many projects are very nicely designed, and you have improved your writing. And the slides I can also see get improved after the midterm exam presentation. That's very good. That's good. So then let's further improve it. And right now you focus on your final project. Okay. Good. You guys hear me, right?
Yep, we hear you.
I can hear you.
Okay, good. Now, feel free to send me your survey if you want. You have any opinions, okay? And I will be happy to feedback to you. Yeah. Okay. Let's get started by today's section. Okay. So in last lecture, we talked about the basics of ray optics. So if we have a lens, this lens is the positive lens, okay? Because the curvature, one side of curvature is convex. If it's concave, then it's negative lens. We will have a slide showing the difference between those two types of lens. Both are very important in the microscope. You will need them both, depending on the question we are asking. Okay. So for the positive lens, if we have an object there, and then this object sitting more than one focal length away from the positive lens, then the light coming from each point of the object, we can determine where they will converge after they go through the positive lens. For example, at the top of the object, this point, the light coming out emitted from this point, we can draw 3 representative paths, and then they will converge at a point at the back of the positive lens. And that point is further away from the back focal point of this lens. Okay, so they will focus here. And this actually is called a real image, because the light coming out from this point really converge here. Okay, this is a real image. It's not a virtual image. Following this principle to draw these 3 representative paths, parallel light, the light parallel to the optical axis, and the light going through the center of the lens, and the light going through the focal point, then you can do the same thing for every point on the object. And then every point will form a real image of that point. Collectively, they form the image of the object, real image of the object. Okay, so this actually is the underlying principle of one lens, how the object form the image. Okay. After that, we talk about the related equation, necessary equation associated with that. Okay, and also we asked you to think about 3 questions, right? Think about 3 questions. Now, I want to ask you, have you thought about these 3 questions? And can you guys give me the answers? First question is, if this object now moving closer and closer towards the lens or towards this focal point, moving closer and closer to this point, what will happen to this image, this real image? What will happen?
I think that the real image would Would it get larger?
Will get larger and larger. That's correct. So you will still form the light going through, passing through the lens will still converge to form an image. But this image will become bigger and bigger. You can join it. When you join it, you will find you move this object closer, and then you still join those 3 lines, and you will find this bigger. That's correct. That's correct. Now, if this guy, question 2, if this object get closer and closer and now sit much closer to this focal point, or even sit on this focal point, then what will happen? Can anybody tell me the answer?
Wait, could you restate the question?
If I move this guy move this one on top of this focal point, what will happen?
Does it invert the image?
You need to
Because you'd have a negative 1 over L2 being negative.
You need to
zooming out so the image gets smaller.
Why the image will get smaller?
Because F is a fixed distance.
Okay.
And if you have L1 being less than F, oh, never mind. 1 minus over L1. So
can
L1's
any
good.
image be formed?
Good question. Good point. Good point. Can you expand your answer a little bit further? Can you expand your answer a little bit further? You hit the correct direction, Eric, right? Eric.
Yeah, so
you are on the correct track.
Would the light rays, I don't think, would be able to converge, but they also wouldn't diverge, so
Exactly.
I don't see how it would form an image.
Exactly. Good. If you see you put the object here, then let's see any point. This point, all the light is going like this way, right? All the light. They have a light going everywhere. They're going everywhere. They also have light going this way, right? So for the light, let me choose a correct color. For the light, like these guys, you see my purple, blue circle here? You see my blue circle?
Yes, I see it.
Those light will not have chance to encounter the lens anyways. So they are lost. They are lost. But the other light coming here, some of them, this one maybe is too far away. So this go away. But this one, it get encountered, right? This encounter the lens. They will go parallel, right? Because they are all coming from the focal point, parallel, right? Right? So then they do not converge, right? They do not form an image anymore, right? And what about the point here? The point here. This point, still at the focal point, this point. What about here? The light coming from this, you can join it, following that 3 paths. You will find the light, let me draw in another color. The light, use the purple color. The point here, all the light coming out from this one will go in this direction. Still parallel, but they have an angle now. They have an angle. Still parallel. They don't form image, but they go in a different angle, okay, rather than parallel to the optical path, optical axis, okay. So the answer for the number 2 is you don't have image. Do you guys follow me?
Yeah.
You cannot guess. You need to join it and follow what I explained to you, the principle. You join it, and then the answer becomes very clear. Okay.
And Dr. Tang, that also aligns with the equation, right? The 1 over F is equal to the 1.
Sure.
Because then that...
Yeah, because that's infinity. Infinity.
Right, right? Yeah, for that to be true.
Let me go back to that one. Let me go back. Yeah. So if you that means that L1 equal to F, right? L1, and then L2 can be infinity, so that this term becomes 0, right? This whole term becomes 0, right?
Yeah.
So that matches, all these things matches, but you need to have that intuition. So good, Erica answered 2 questions. One is when the object is closer, moving closer to the lens, how the real image looks like. It's become larger. That also implies if you move this object further away, then how this image look like, right? If you move further away, what will happen? Then this one, if you move away this object, you see my cursor or not? Do you guys see my cursor?
I see it.
Okay, if you move this away, what will happen? That's the question. Now, to answer that question, we can move this guy to extreme point, move this very, very away, further infinite away. Then all the light coming from this will become parallel light, collimated light that are parallel to the optical path. Then all the collimated light will be focused on this focal point, back focal point, right? Do you guys follow me? Do you follow me?
Yeah.
Yeah. Then that means from this point, current point to the infinity, as you move away towards that infinity, this current real image gradually shrink until it becomes 1 point here, right? So when if you move away from the focal point, the real image reduce. If you move closer to the focal point, the real image increase. That's question number 1. If you move, and then question number 2, if you move toward to be exactly on the focal point, there will be no image. There will be no image. Okay, this is the intuition you need to form when you design optics. If you have this intuition, you will know how to place your lens, place your mirror, place your sample. Okay, this is very important. The way to form this intuition is you need to draw the light path as I explained there. Okay. Now, then question 3. What if the object is at a 2F position? So here is 1F. If the 2F, then the position will be at this point. What about this point? If the object is here, what is the image there? Can anybody tell me the answer?
Is it just its standard size with no magnification?
Be more specific. You hit some point now. Is the what is the real image still inversed or not inversed? Be specific.
I was just thinking for like the magnification equation, thinking that if it's 2F,
yeah,
L1 is 2F, then L2 has to be 2F. So your magnification is just 1x.
Excellent. So that means magnification is 1, right?
Yeah.
Magnification is 1. And then the position of the, what is the position of the image? Also 2F, right?
Yeah.
So they are symmetric, anti-symmetric in between the with the glass, but it's still inversed, right? Think about the equation. Yes, that's correct. But the equation only tells you the L1, L2 with relation to the F. You need to know the real image here, real object, what is the image of it at the function of the distance. Okay. Jackson, very good, very good. You move a step further now. So I asked 3 questions. Erica answered 2 correctly. Jackson answered 1 correctly. That's good. How about the other students? Do you guys follow us?
Yeah.
Okay. Okay, good. Now, what does this tells us? If you have 1 lens here, if you only have 1 lens, then you have the sample. How many of you used microscope for the research before? How many of you used microscope for the research?
I do.
You do. Okay. Now then I have a question for you. In the real microscope, when you do the image, this lens is the microscope objective from different companies, Olympus, Zeiss, and the Nikon. Now you have the cell in this sample plane, right? In the sample plane. Now, if the cell is here, and as we said in the question 2, there's no image formed, right? So then in the real microscope, how can we get the image at the camera here? If we have a camera here, how can we get the image?
By having more lenses behind it.
Excellent. So they actually, in the real microscope, there are many, many different lenses. So they are keep relay the image from the object to the real image, and then again to the real image to the real image, and then real image to the real image. So many, many times until they find the hit to the camera chip. Okay, good. We will have a very detailed diagram to show that, and that is very that can be very manipulatable. When you see that, you can understand the meaning better. Okay, good. Now here is the ray optics for one lens, and then following that 3 questions, if you go past that focal point, if the object has the distance even smaller than the focal length, than the of the lens, then it get even closer. Then what will happen? In that case, if you join the 3 paths I just mentioned, you join it, you will find the light penetrating through the lens will never form any converged image anymore. Rather, they will diverge. That will diverge. But if you join those diverged light reversely to an opposite direction, you will find they will converge to a point that is further away from the object. Okay, so that converged object is called a virtual image. It's a virtual image. So that means you will never have a real image formed by this lens. But those light, if you look at them from the right-hand side, you will see those light seems likely emitted out from this virtual image. Seems like they are emitted from this guy. And then their size is even larger than the object, okay? So that's actually the mechanism of magnify. If you hold one piece of lens closer to the piece of paper that contains very small sized font, small sized words there, the older years book, right? Very small text there. Then you actually use this lens, let the light scattered from the text form a virtual image, and then that virtual image is perceived by your eyes. Okay. I saw a question here, Laura. So okay, so I see that the best solution of the image would happen when the light ray converge. If this is the case for all microscopes, how come some can contain better resolution than others? Good question. So what Laura was asking is how can different microscope have different resolution? Okay, so that actually comes from a different material. Laura, you hear me?
Yes, I do.
Yeah. What you are asking actually the factor you mentioned, different resolution, that factor still follow the principle we discussed here. The ray optics still apply, but in different microscope, they have different lens. The lens size will change. Lens quality will change. That give the and the lens's curvature will change. Those curvature will change. That give the different objective, different numerical aperture. Numerical aperture is the indicator to tell people how much light coming out from this object can be collected. Okay, can be collected. If as I drawn here, any object, they have a light going different directions. Going different directions. If you want to have a higher resolution, you want to capture as many photon emitted out from this object as possible, so that those light will not get lost. Okay, so higher numerical aperture, actually you get more light. You get more like this side. Okay. So we have some slides at the back. The resolution actually coming partially from the wave optics. If you get a worse resolution, actually many light you collect you don't collect it, you lose that. Then the remaining light actually will interfere with each other, cause the feature become very blurred. Okay, it may I can show you in the next few lectures. Then you can see the difference there. The key point here is the different resolution depends on the optics there, different quality of the optics you use in the microscope. Okay, you hear me, Lola?
Oh yes, thank you. That makes sense.
Sure, good. But overall, the resolution still get limited by they still have limitation. No matter how you make the optics, they still have limitation, because these optics here, they cannot capture anyway. By all means, they cannot capture all the light from the object. Okay, they at most collect only half of that. Okay, so if you want to do better resolution, another way people use is they put two objectives here. One is on the top, one is on the bottom. Okay, so you have another objective here, another lens here, collect the rest half of the light, and then combine these two lights together in the computer. So then you can get a much better resolution. Okay. So this is beyond what I wanted to discuss at this point. Okay. Now here what I'm showing is the virtual image. Okay. Now based on what we discussed here, we need to know how to manipulate the light. In the last lecture, I mentioned when I show the pinhole that allow the reimage of the standing lamp, right? I show that pinhole. I mentioned the two important terms, position and angle, right? That can be that their importance can be appreciated here now. So here you see the object in front of one lens, and then you may notice some interesting relationship between position and angle. Now this object, we purposely put it on the focal point, this green dots here, put it purposely here, okay? So that all the light coming out of from this point, you can see that they emitted. So we still draw the three lines, except the three major paths, except the third path, we cannot go through the focal point anymore, right? We can draw another line that is just lower than the first two lines. So you can see that for all three lines, if you let them go through the lens, you will see they go out after they penetrate through the lens. They are parallel to each other, but now they are not parallel to the optical path, not parallel to this optical axis, right? Now, what does this mean? This means if you move the position of the sample from the focal point to a different position, then you will correspondingly change the angle of the light passing through the lens. Okay, if you have a point here on the focal point, you have sample on the focal point that is sitting exactly on the focal point, then the light coming from it and passing the, let me see, passing through the the lens will be look like this. Do you guys see my drawing?
Yes, I
Yeah.
see.
if you put the sample directly in the focal point, then the light passing through the lens will be parallel light, and is parallel with the optical axis. But if you move this point to different position, still one focal length away from the lens, okay? You move it up. Then as you move away, the light passing through the lens will start to tilt away from this purple light. And then if you move the sample point to this point, to position A, then the light will be around those red light, okay, around this red light. So that's actually is an important relationship. That's the relationship of position and relationship of angle. That's very important. What does this mean is if you have a cell here, okay, you have a cell, or you have many cells, many samples here. So here I put the cell vertical, but in the real imaging, in the microscope, you do it vertically, right? Here I actually flip it 90 degrees. So you have many cells here, many cells here. Now all those cells are fluorescent, and then they emit out the light. The cell at the close to the center here, those regions, they are light, mostly is horizontal light, and or maybe a little bit of angle change, okay, if they are further away from this focal point. But if the cell is too far away, then the light is bended too much after they passing through the lens. Then you have an objective here. You always have an objective. So objective will never be able to collect those red light anymore, right? So they will lose the information of the cell further away, far away from the focal point, right? So that's actually the highlight one important hallmark of the microscope. You need to make this one is very important. This objective is very important. You need this one to be big enough to capture as much information as possible from the cells on the sample plane. Okay. Now, do you guys hear me?
Yeah.
Yeah. So now, very good. This is just one point. You can also do it reversely. This principle can also be used in a reversed way. Now, if, which is shown in these slides. Oops. These slides. Yeah. Here. Oh, here is the same thing. I show you see the angle change from the green point go up to the blue point. You see blue point has a slight tilt with respect to the dashed line, the optical axis, right? But if you go up to the red point, then the red line is even more tilted compared to the optical axis, right? So that's the point I want to illustrate. And then the second point I want to illustrate is this relationship also be used in the way that you can selectively expose cells or the object with light. So yeah, they work in a reverse way. So this is actually working in the two directions. Now let's go back from the parallel light to the object in a different way. Then that's very useful in the laser scanning microscope. So if you have an object on the sample plane, you want to expose that point only with the light rather than other point. Then the way to do is you can arrange the angle of the incoming light so that they will converge and focus on that point. Okay, if you have the angle of if you have an angle of your incoming light parallel horizontally go this way, then they will be able to illuminate the cells that is also in the center of your field of view. But if your object of interest is away from the center of the field of view, then if you want to illuminate that guy, what you need to do is not to move the lens. You don't move the lens, and you do not move the light. You rotate the light. You tilt the light. Then it will go to that point. Okay. I mentioned when I talk about that timeline of the optics, there is one very important discovery, or important invention, that is a confocal microscope, right? In the confocal microscope, the first confocal microscope is called a laser scanning microscope. So that actually is people use a lens at the position it on the light path, and then that lens is connected with a motor, so that they can rotate that lens, and the light will be reflected by that lens. If the mirror is rotating, it actually rotating the angle of the laser beam. Okay, and then that mirror can rotate in the X direction and the Y direction, so that they rotate the angle of the laser beam in the X direction and the Y direction. What it end up with is it will be able to scan all the point, 2D point on the plane, on this plane. Okay, so they will scan X direction point, Y direction point. Okay, this is called rastering. Okay, so that the people can do the confocal imaging of a sample in the very sharp manner. Okay. In addition, if people wanted to do the selective imaging, for example, if you have a big tissue there, you do not want to have the background from the surrounding tissue. Tissue imaging is different from the petri dish imaging. Tissue imaging, you have cells all surrounding it. It's very noisy. If you want to just get one sample, one cell's results from it, and wanted to minimize all the background information, then you can use this kind of scheme. You can let the light go manipulated by the mirror, and then focus on the point that is the cell of interest, and then let this light be the infrared light. So then in the infrared light will have a large wavelength red color photon. Then when those light get focused on this point, there is a chance two red photons will collide with each other, and then they will form a blue photon. Okay, that is the idea of a two photon. Then only that blue photon can stimulate the cells, because cells will express GFP, right? Green fluorescent protein. And then that blue photon will stimulate GFP. So then this cell will emit out the fluorescence. But the surrounding cell, they are not exposing the light. They're not exposing the light. They only expose the red light, right? And the red light is not focused to generate a blue photon in other position, except the focal point, right? So then you can get the signal exactly from the cells within a bunch of tissues. And then you can rotate the angle of the light before the lens, so that you can scan different position, X, Y, different position. Okay, and then you can change you can also shift in the Z direction, so that you can see the whole X, Y, Z single cell within the tissue. Okay, so this principle, what I'm saying is this principle is very simple, but it has a very profound meaning in the real experiment, real operation. Okay, now, oh, by the way, here I also mentioned the stat. This I didn't mention. Do you guys know stat? This is one super resolution technique. Do you know this? If you don't know, that's fine. Doesn't matter. I can explain it in the future. Okay. Do you guys hear me? So far, so good?
I'm not familiar.
Okay. So far, so good?
Yeah, so far so good.
Good.
Yeah.
This is a stat is one type of super resolution. Maybe let's save the time. I can explain it to you in the future. Okay. Okay. Now there are some more knowledge very useful. I mentioned this before. The lens has two types. Okay. So one is called positive lens. The curvature is convex. Okay. So then they can converge the light to another side of the lens. Second one is called negative lens. So then they actually don't converge the light, they diverge the light. So once they diverge light, the light will not form any real image. But if you look at look at those, they actually light is seems like they are coming out from some virtual image at the front side of the negative lens. Okay, so that's the properties of negative lens. This is a very broad category. This is just two. In the reality now, when we do the experiment, we can generate a mixed positive and negative lens depending on your experiments. You can mix them together. Okay, in one lens you can fabricate it that way. Okay, and even for the positive lens, you can fabricate it to have convex curvature around X, and then zero curvature around Y direction. Okay, so then you actually get a cylindrical lens. Then it's not a spherical lens. So what does that mean? If you have a this is a spherical lens. If you have the light go pass through it, in this picture only show the planned view, right? But if you have a light going through it, then it's like a spherical shaped around this surface. Then they will focus on one point, right? But if you have if you have this surface still remain convex curvature, but in the horizontal in the orthogonal direction, you let it to be flat, means you have zero curvature. Then on that direction, you will not focus anymore. Okay, that's called spherical lens. Let me show you one example, then it's very clear. So if you have a lens like this, do you guys see my drawing?
Yeah.
So you see, if you have a one like this, what if it's a spherical lens, then it looks like this. Spherical, but here is more curved, right? And more like this. You understand my point? Spherical lens.
Right.
Then, for this guy, if you have light coming in, it will focus on at one point at the back. But for this one, if you do coming light, what will happen?
Focus in a line.
Exactly. Excellent. It will focus on a line. Okay. So there are many of those lines there. So there's a line here. Okay. In fact, it's not a line. It's not a line. Because the light will go like this way. It will go like this way. So in fact, it means here you have a certain width here. You still have a certain width. It's not a point. It's not an exact point. If you focus on this one, if you magnify this point, the light actually have a Gaussian beam here. It has a Gaussian beam here. Okay? And within, if you zoom in to this point, inside of this point, there are many interference, light interference there. It has a special pattern inside. I have a slide showing that. You don't worry about it. Okay, so it actually has a pattern here, and then this width is hundreds of nanometer. It's not a point. Okay, that means here spherical lens is actually not generating a line. It's generating a sheet. It's generating a sheet like this. It's a sheet. Okay, generating a sheet. This distance is hundreds of nanometer, and this distance is the same size of the width of the objective of the lens. Okay, so all what I'm saying is in our class we want to emphasize fundamental basics of optics, but once you understand that, you can easily understand many more sophisticated application in our lab or in other labs. Okay, so far so good.
Yep.
Okay, good. Now that's the lens, and then here are some more physics about the light. That is the refractive index. So refractive index actually is the property of the material, of the transparent material. It shows, it will show how much light will get reflected once it passes through that once the light go from the air into that material. So on the right hand side, this is the basic physics you may have learned in the high school, right? In the high school or middle school. So the light, incident light come in, some of the light get reflected, and then on the surface, and then these two different materials have two different refractive index. One is the air, one is the water or the glass. Okay, and then because this N2 is larger than N1, so then the light actually get bended. Usually the light get more bended, then more means what? More means I compare this light with this direction, with the direction that they do not change the direction. Okay, so if the N2 is larger, then the light get more bended away from the original direction. Okay, and some of the light definitely will get reduced due to the reflection. Okay, so and this angle and the refractive index of two different materials satisfy this equation. Okay, so that's the definition. So any material that has a refractive index different from the air, they will always cause the light to change their direction. That's the internal material behavior. Okay, and then because of this change, they also can change the light path within the material. That can change the speed of the light. Okay, so the frequency of the light will not change. They will change the direction, change the speed. Okay, when they penetrate through different transparent material. Okay, and those are the relationship between the speed and the material's refractive index. Here we use the light speed in the vacuum as a reference. Okay. Now this I don't need to talk more. I guess you know, but if you have questions, you can ask me. Okay, this is a very fundamental but very useful knowledge. Yeah, and then okay, here are some examples. Here are some examples showing the different material. They have different refractive index. Okay, here I have a question. How about the refractive index of immersion oil and cover slide? So this question asks about this glass cover slide and the refractive index oil. You can see here they are the same. The best immersion oil and the refractive index is the same as usually as the glass cover slide. They are the same. The reason, what's the reason? The reason is because when we do the microscope imaging, you want the light do not bend. You don't want them bent before they enter the imaging objective, because when the light is bent, you will lose the photon. You will lose the photon, and all the photon from the sample is useful. So then people actually always use the immersion oil on top of the cover slide, so that use the immersion oil to replace the air. Okay, so then the light will not get bended and be completely absorbed, collected by the microscope objective. Okay, so that's the answer for this question. Okay, now okay, here are some important terminology. I actually mentioned this already. Important terminology. Talk about the optical path length. That's actually not very useful for now. This is the theory developed several centuries ago. Optical path length is equal to the real length, real travel distance of light times the refractive index of that material, times them together. Okay, so then in the next slides, many centuries ago, Feynman developed a principle. Feynman's least time principle. He developed this principle to demonstrate, to understand why all the light goes through the lens will focus on one point. his point is even on the lens, you see here the lens, you have different thickness, right? Lens, usually the possible lens in the center is thicker, edge is thinner. His question at that time is several centuries ago. He want to know why after light goes through this lens that contain different thickness, they still focus on one point. And also not only focus on one point, all the light coming out from the lens, they actually arrive this focal point at the same time. Why? He want to know that. And then he figured out that is because even the distance that for the light to travel in the air and in the lens are different. But if those lens correspondingly times with the materials refractive index together, then they are equal. So that the light on the top that goes through the periphery of the lens, these things travel longer in the air than the light at around the optical axis, right? This travels less than this lens. But in the center one, they actually travel longer distance in the optical lens. And then this optical lens, because they are made of glass, they have a larger refractive index. So then collectively, their optical lens is equal all the light. So then that's why they all converge and arrive at the focal point at the same time. Okay, this is a very useful principle. But in the real optical design, we actually don't need to use it. This just explain why they converge at one point. Okay, and then Feynman also this is the story he put. You can read it. Okay, now most important is this one. All what I'm talking about to discuss about the refractive index actually is want to lead to the TURF microscope. So we mentioned the TURF microscope here. If you understand the refractive index principle, then you can understand what is TURF microscope. So this the full name is called total internal reflection. Do you guys hear me?
Yeah.
Yeah. The mechanism is we have the sample. We will have the sample in the liquid. Okay, in the liquid. Now, if we take one step back, let's take one step back. When we talk about the refractive index, the definition, we actually have the light go from N1 to N2. N1 is air, N2 is the water. Okay, so it's then the light get banded away from the original position and then closer to the vertical line. If we go in the reverse way, we let the light go from a material that has a higher refractive index and then go penetrate into the material that has lower refractive index. Then the light actually follow the path that will bend. It will bend even further away from the vertical line, from the vertical normal direction. Okay, so here shows the example that three material. If we let the light go from the water to the glass, then the refractive index is from 1.33 to 1.5. So it's going into a denser material. So then the light will bend towards the vertical line, right? Towards the vertical line. But then from the glass to the air, it will bend away from the vertical line. So it will go this way, okay? Go this way. Now, in the real experiment, in the imaging, you actually let the light go from the glass into the water, such as showing here. When we have the sample, let me see. Maybe this one is better. Yeah. We have the sample show in the petri dish. The cell is in the petri dish. Now, we need to use the light to excite these cells. So then the light will come out from the objective. And then the light go by all means through the glass bottom petri dish, will penetrate through the glass. and then get it into the water. Because the water has a lower numerical lower refractive index, then the light actually bend further away from the original position, right? So it will go closer to the surface of the petri dish. So the light going from, so you have the surface here. The light come here, it will bend this way. So here is the water, and we have the cells here. Here is the glass petri dish. This is the glass petri dish. Okay, so the light will bend this way. Now, if we let the incoming light to be bended even further, then this light, when it's coming out, it also will bend even further, right? And at some point, if you bend it go this way, it will be reflected totally this way, right? So this actually is called internal reflection, total internal reflection, TIR. Why this is useful? Because this is useful when you have cells cultured in a petri dish, and this is the media, right? Here is all media. Those media sometimes contains many autofluorescence sources. What we are interested in is only this cell. So you only want to let the cell be excited by the incoming light, and then the fluorescence coming only from the cell is of interest. So then you direct the light to let it totally reflect. And then when the light totally reflects, they actually will generate at this heating point. At this heating point, do you guys see my blue part? Blue joining here?
Yeah.
Yeah.
At this heating point, the light will convert its mode. It will convert from the light is transverse wave. It will convert from the transverse wave into another wave called evanescence wave. That wave will quickly decay from the surface, but it will penetrate through the surface. So if you magnify this part, you will see this part has a wave going this way, this way, this way, this way, this way, exponentially around the z direction. Around the z direction, the intensity of the light, if this is the intensity of light, will exponentially decay. And at this distance, before it decay to zero, this distance is about tens to hundreds nanometer. Okay, and within this distance is sufficient to illuminate the bottom of the cell. At the bottom of the cell, what are there? The membrane, the ion channel, the integrin, the transmembrane protein are there. So then, at this bottom of the cell, so the bottom of the cell here are all illuminated, and above hundreds of nanometer, above here, those samples do not receive any light. They are not excited. So you will get a very clean background, only have a high signal at the interface between the cell and the bottom glass petri dish, right? So this is the beauty. You use a very simple way. You take advantage of the factor that the light will bend and will bend downwards when the light go from the glass to the water. Then you let it totally reflect, and then only excite tens to hundreds nanometer thickness sample, biological sample, and then collect that information there. Okay, that's the beauty. So here is the photo, the real diagram. It's a real diagram. Yeah. So here's a real diagram. So if I light goes through it, you have the evanescent wave. Okay, evanescent wave that will excite the cell close to the surface. Okay. So this method is called total internal reflection fluorescence, TIRF microscope. Okay. Now to do that, you will use the same method I mentioned, angle to the position. So at the microscope in this red color is laser, you will change the position and then change the angle here. When you change to a certain angle, you will let the light totally reflected. Then you get this TIRF microscope. Okay. Once you have this, you will start to see the signal like this. Here is actually many fluorescent microsphere on the surface. You see here, on the top is turf, on the bottom is not turf. On the top, you see my cursor, you guys see my cursor?
Yeah.
Yeah. On the top, you see the figure B. This is the fluorescent picture of the fluorescent microsphere. You see the very clear sphere, and the background is all black, right? Background is black. If you don't use this, you use the epifluorescent microscope. You let light go through directly towards the sample. Then you see the surrounding media also get excited. Surrounding things that is above that 100 nanometer material, they also get excited. They will generate autofluorescence. Then their background is very noisy, very white, right? Then the signal to noise ratio means the bright point divided by the noise surrounding point is about 1.3. But this one, you see the turf one, you get a signal to noise ratio 35. So it's 10 times more, 30 times more, right? So that's much better. And then in the reality, you can use that to see the focal adhesion, means integral, the collection of integral very clearly. So this is the turf. This is not a turf. This is not turf. Okay, you see the very blurring. A is not turf, B is turf. And then in the cell structure here on the A, you see all the cytoskeleton is epifluorescent. You see everything, but you may also get a lot of noise there. If you use turf, then only the cytoskeleton, you see here, center part and the periphery part, they are very, very close to the glass bottom petri dish. Very, very close to that they are within that 10s to 100s nanometer region. They are excited, but the other part, they are not excited. So the signal to noise ratio is very good. Okay, so this is the advantage of turf. It's very useful to study some structure that can be located close to a surface. Okay, sometimes that surface matters. You want to understand the surface, then you should use the turf microscope. If not, if you are interested in the other region, other position, then we need to redesign the microscope. We see the other structures. Okay, good. Now it's 4. I need to stop here, and we will continue those exciting topics Monday. Then, yeah. Oh, Monday we have the invited talk. Okay, yeah. You guys hear me?
Yes, I hear you.
Yep.
Excellent.